What's up? I'm Vin, and today we're going through this AP Calculus ABBC Unit 8 practice test, and I'll leave a link to a copy of this test in the description below. Now let's get started. So for the multiple choice questions here, we are going to use a calculator for just these questions over here. And first up, we have Hank, a professional hot dog eater, can eat hot dogs at a rate modeled by the function R of t, where R of t is measured in hot dogs per minute, and t is the number of minutes from the start of the hot dog eating contest. And we want to know which of the following expressions gives us the average rate that Hank eats hot dogs from t equals 5 to t equals 8. So for this question here, we have to make sure that we choose the correct formula. So the two formulas that I think of when I hear the average is I think of the average rate of change formula. So the average rate of change formula, we would have f of b minus f of a over b minus a. Okay, so that's the first formula that I think of. And we learned this like early in the course. This is technically even an Algebra 1 formula, but it shows up in calculus a lot. And then the average function value, so average function value, this formula we have to know as well. So the average function value formula, we have 1 over b minus a times the integral from a to b of f of x dx. So for these questions, the dilemma is, oh no, which one do I use? So well, the trick is you have to think about which formula or function did they give you in the beginning. So they gave us R of t, and they told us that R of t was the rate that Hank eats hot dogs. Okay, so what we have R of t, and once again, R of t is the rate that Hank eats hot dogs. Okay, so we'll just say the rate like the hot dog rate here. Okay, so this is the rate that Hank eats hot dogs. So if we're trying to find the average rate that Hank eats hot dogs, we're going to be finding the average value of the function R of t. Okay, so that tells us, let's just make that a little bit neater, we're going to be using the formula on the right here. Okay, we're going to be using this formula, and we're going from t equals 5 to t equals 8. So we're going to go with, once again, this formula. This formula here is no good. So we're going to go with the average function value of R of t. So the average value of R of t from t equals 5 to t equals 8 is going to be 1 over 8 minus 5, and then we have times the integral from 5 to 8 of R of t dt. Okay, so we're finding the average value of R of t. And once again, R of t is the rate that Hank eats hot dogs. So now we just go ahead and simplify this. 1 over 8 minus 5 simplifies to 1/3, and we have the integral from 5 to 8 of R of t dt. And now we just scan the answer choices here, and this matches up with choice B. Question 2, one day in April, the temperature in San Diego, California, in degrees Fahrenheit, t hours after midnight, and we're saying midnight is t equals 0, is modeled by the function f of t, and here's our function for f of t over here. And then we have, on this April day in San Diego, what is the average temperature between 2 a.m. t equals 2 and 8 a.m. t equals 8 in degrees Fahrenheit? So this, once again, we're going to be using the average function value formula. We're finding the average value of f of t from t equals 2 to t equals 8. So we're going to have 1 over 8 minus 2, and then we're multiplying by, so let's just make this a little bit neater. We have the integral from 2 to 8 of our function f of t. Okay, and I'm just going to write it like this, but yeah, technically what I'm typing into the calculator in a moment is this entire expression here. Now, one thing to mention before we move forward here, make sure that you are in radians for the entire AP Calculus test. So now we're going to type in this fraction here. So I'm going to have alpha y equals enter to pull up a blank fraction, and we have 1 over, and let's pretend we don't know 8 minus 2 is 6. So we could just type everything in exactly like this, and now we're going to press math 9, and our integral is going from 2 to 8. And now we just have to type in the actual function for f of t. So f of t, we'll write this over here. We have 70 minus 10 times cosine, and now the inside here we have pi times t, but we'll go ahead and use x. We don't have to use t. So pi times x divided by 16. Okay, we could close the parentheses here, and now we get outside and we type in dx. And now just press enter, and we can see that our answer is going to match up with choice A. Question 3, we have a particle moves along the x-axis, and then we have the velocity of the particle at time t is given by this function here, v of t. And then we have, if the position of the particle is x equals 3 when t is equal to 1, what is the position of the particle when t equals 4? So let's say we call x of t the position function. Our goal is to find x of 4. Okay, so this is what we want. And right now what we know is we know that when t is equal to 1, the position is x equals 3. So that tells us that x of 1 is equal to 3. So our goal here is to find x of 4. And we're starting with the velocity function. Well, one thing that I think about with position, velocity, and acceleration is the order of things. Okay, so we have to know that position is essentially the starting function. Okay, so we have the position function, and then we take a derivative with respect to time, and that would tell us the velocity function. Okay, so that would tell us velocity. And then we take another derivative with respect to time, and this is going to tell us acceleration. So I'll just abbreviate this part here. So considering that we're starting with velocity and we want to say something about position, we have to do the opposite of a derivative. We're going to do the antiderivative to talk about position here. So we're going to be finding the integral of velocity. And now what I like to do for these questions, let's say that you forget the basic formula, or this is not necessarily a basic formula, but if you forget the formula for how to just find this directly, one formula that you absolutely need to know for the AP Calculus exam is the fundamental theorem of calculus. Okay, that you should not forget. So this formula, the fundamental theorem of calculus, we could use this here. And our goal, once again, is to find the position at 4. So I put the time that I want to find the position at, and then I put the time of the position I know. Okay, so I know what the position is at t equals 1. So I put the one that I know and the one that I'm trying to find up top. So now we apply the fundamental theorem of calculus. And remember, the multiple choice, you don't have to say like what theorem you're using. You could just apply the theorem. But what we're going to do is we're going to anti-derive velocity, and that's going to give us the position function, which I'm naming x of t. So this is going to give us, we're going to have x of t, but evaluated at t equals 4 and t equals 1, and we subtract. So this I could just say is equal to x of 4 minus x of 1. So once again, this is the fundamental theorem of calculus, which we cover in Unit 6. Okay, so this is something you should be very comfortable with. If not by this test, make sure that you really practice the fundamental theorem of calculus because it's going to show up on the AP test a lot. So now, once again, our goal is to find x of 4. So I'm just going to do a little algebra here and add x of 1 to the other side. So now I'm just going to say that x of 4 is equal to, and we're going to have x of 1 plus, we have the integral from 1 to 4 of v of t dt. And now this I could simplify a little bit more. X of 1, we were told, is equal to 3. So I have 3 plus, and now I have the integral from 1 to 4, and our velocity function is t squared plus 1 over, let me just make that a little bit neater. So we have t squared plus 1 over, and then we have e to the t. And then we just tack on our dt here. Okay, so this is the actual expression we're going to evaluate in the calculator. So now let's type this in. We have 3 plus, and now we'll press math 9, and our integral is going from 1 to 4. And now for the integrand here, I'm just going to press alpha y equals enter to pull up a blank fraction. And we have t squared plus 1, but we're going to use x. So you have x squared plus 1 over e to the x. And now we just tack on the dx at the end. And now we press enter, and we'll have our answer. So now rounded to the nearest thousandths place, we're going to have 4.713, choice D. Now, one thing I want to point out here, let's say that you forget this initial condition. You forget to do 3 plus. There is most likely going to be an answer choice waiting for you. But be careful, choice B is a very dangerous bet. Once again, make sure that you consider the initial condition when you are looking for your final position. Question 4, we want to know what is the area of the region in the first quadrant bounded by the graphs of x equals y squared and y equals x. So for this question here, it helps to be able to sketch these basic functions. And for this one, it's a little bit tricky because it's a function of y, not a function of x. But x equals y squared, I'm automatically thinking of a parabola like y equals x squared. So anytime I see that function, I'm just thinking of this. But since it's x equals y squared, it's just going to be facing sideways like this. Okay, so here's x equals y squared. And now y equals x, that should be an easy line for us to graph here. Okay, this is just going to be the line going like this. And our goal is to find the area of the region in the first quadrant bounded by these two equations here, or these two functions. Okay, so we have this space here is what we're looking for. Now, I know technically, once again, this is not a function of x equals y squared, but we can call it a function of y. But in either case here, they're telling us to find the area of the region bounded by the graphs of these two equations here. But that's just a small detail I want to mention, that technically this is not a function of x equals y squared is a function of y. So now what we want to do is we're going to take a cross section. And since we're dealing with the function of y, we're going to take horizontal cross sections like this. And now the key is to describe the area of one cross section. We have to think of how we find the horizontal distance between these two curves. And notice here that this equation I could call x equals y. And the equation over here, I'm going to call this x equals y squared. And if I want to find the horizontal distance between these two curves, I'm going to do the curve on the right minus the curve on the left. So I'm going to do y minus y squared. Okay, so that's the horizontal distance going this way. And then this small vertical change, I'm going to call dy. Okay, because remember, dy delta y represents that infinitesimal change in the vertical direction. So if I want to describe the area of this thin rectangle, I'm going to call it dA. Okay, this represents the area of this thin slice. So the area of this rectangle is base times height. So I'm going to do y minus y squared multiplied by dy. Okay, but this is just the area of one slice. I want to find the area of the whole thing. So this is where I have to consider the intersection points. And in this case, it works out nicely. The intersection points are 0, 0, and 1, 1. And in this case here, if you mix up the x's and the y's, it doesn't matter because the x and y limits are exactly the same. So moving forward from here, what we could do is we're going to just set the limits here to be 0 and 1 because that's the bottom of the interval here. Is it's starting at a height of 0 and the region ends at a height of 1. Okay, so when you're setting up your integral in terms of y, you want to focus on the y coordinates of your points of intersection. So now we're going to take the integral of both sides from 0 to 1, and let's just say that the area of this region is capital A. And now I apply the fundamental theorem of calculus. The antiderivative of y is 1/2 y squared. And then I have minus the antiderivative of y squared is 1/3. And then we have y to the third. And I'm evaluating this from 0 to 1. So now I'm going to write that result over here. We plug in 1, and we're going to have 1/2 times 1 squared, or just 1/2 times 1, minus 1/3 times 1 to the third, which is just going to give us minus a third. And then I have to subtract. If I plug in 0, I'm going to get 0 minus 0. So this part here is just going to cancel out nicely. And now I'm going to make common denominators. I'm going to multiply the top and bottom by 3 to get 3 over 6. Minus, for this fraction, multiply the top and bottom by 2, and you get 2 over 6. And now 3 over 6 minus 2 over 6 is equal to 1 over 6. So that is the area of the region highlighted here, is 1 over 6. So we're going with choice A. Question 5, we have the graphs of f of x and g of x shown below, and we want to know what is the area of the regions bounded by the graphs of f of x and g of x. So anytime you want to find the area between two curves, the concept is top minus bottom. So here we have the graph of f of x, and that's the cubic function, the one that's turning like this, the graph in red. And then the bottom function in this space is g of x. But then notice that after this region here, we have another region where the curves are bounding an area over here that the roles reverse. Now g of x becomes the top function, and f of x becomes the bottom function. Okay, so the long way to do this, and then I'll show you a cool shortcut, but the long way to do this would be to find the area from A to B, so that's the beginning and end of the first region. So we'd have the area from A to B, so we would do the integral from A to B of the top function f of x minus g of x. Okay, so that's the integral we would be setting up here, and that would tell us the area of this first region. And then we would add, and let's just say that the end here is going to happen at C, even though the graph is telling us it's going to happen at 2. But let's say it ends at C. Then we would have the integral from B to C of the top function in this region is g of x minus the bottom function is f of x. Okay, so if we use this idea, that will tell us the area of both regions. So the first thing I would do for a question like this is just type f of x and g of x in the y equals. So now we press graph and we get a picture of what's going on here, but a nice little feature you could use, you could press zoom number 1, that's zoom box. And what you do is it's like cropping a photo. You put one corner where you want to start your, cropping of the photo. You press enter and then you drag down and over and you get the rectangle that you want. And this is going to give you the window that you're going to use in a moment. So I personally like to zoom in using this feature because it gives you something very precise. And now when I press enter, notice that I get a very nice picture of what's going on. So now to be 100% precise, we just have to know where do these curves intersect. Now it might just be obvious from the graph, but I'm going to be super precise. I'm going to press second trace number 5. And let's say that I can't see that this is happening at x equals -half. Then I just go near the intersection and I press enter 3 times. And you see how at x equals -0.5, that's the first place where these curves intersect. Now, the second place that they intersect is at x equals 1. And if I press second graph, notice here that when x equals 1, we have matching y values. And then the last intersection point is happening at x equals 2. So if we go back to the main screen now, remember f of x we typed in the y1 spot and g of x we typed in the y2 spot. I could go back to the main screen and now I'm going to do math 9 and I have the integral from a to b. But remember, our intersection point, our first one was at -0.5. So we have -0.5 and the region ended at x equals 1. And what we have is for the first region, it's f of x minus g of x. So a nice little shortcut you could use, you could press alpha trace, y1 is option 1. And then we have minus g of x we typed in the y2 spot. So I could press alpha trace and then y2 is number 2 like this. And then I press dx. So now I'm going to add the second integral. I'm going to press math 9. And the second integral, we're going from b to c. And remember, the other two intersection points occurred at x equals 1 and x equals 2. So our limits are going to be 1 and 2. But remember, the roles reversed. Okay, then it became y2 minus y1. Now, let's say you don't have that alpha trace shortcut. You could also press vars, go to the right, go to function, and we're doing y2 minus, and then once again, vars, go to the right, we go to function, and then y1 is option 1. Okay, we do this, and we just type in our dx, and we press enter, and this is going to give us our solution to this example. Now, I just want to show one really awesome shortcut. Let's say you don't even want to think about top minus bottom because this is a calculator question. What you could do is, notice the beginning of the interval was at x equals -half, and the entire area ended at x equals 2. So let's say you want to do it all in one shot. Then the trick is you're going to use absolute value. You're going to press math, go over to number, and then go to absolute value. And then it doesn't matter which order you use. You could do y1 minus y2, or you could do y2 minus y1 because the absolute value is going to correct it anyway. Okay, so remember, if I, once again, just use the absolute value, it's going to do everything in one shot. So I'm going to do y1 minus y2. So I have alpha trace, and I'm going to type in my y2. And this is just a really nice shortcut, and it should give us the same answer. And notice that it does. We're going to get 2.635. So our solution to question 5 is choice C. Question 6, consider region S bounded by y equals square root x and y equals x squared. And we want to know, what is the volume of the solid generated by revolving S about the x-axis? So for questions like this, the first thing I like to do is highlight the axis that I'm spinning around. So in this case, we're spinning around the x-axis. And now we want to think about, are we using a disk or a washer? But we're not going to be using a disk here. And the disk is the cross-section where it's completely solid. And we use the disk when there's no gap between the region that we're spinning and the axis that we're spinning around. Okay, so in this case, notice there is a space. So that tells us we're going to be using the washer. Okay, so the washer is kind of like the disk, but there's a hole cut out in the center like this. Okay, so that's the cross-section that we're dealing with when we revolve region S about the x-axis. All right, it helps if you could kind of visualize what this thing looks like, but this is kind of hard to draw. I just imagine like if we take region S like this and it's being rotated, it's going to make some sort of, yeah, I'm not the greatest artist in the world, but you might be able to visualize it. It's easier to visualize when you have something like, let's say you have a rectangle and you revolve this around an axis over here, you could see that this is going to turn into a cylinder. Okay, so when it spins, this is going to turn into a cylinder if we were to spin it around. All right, so that is a little bit easier to see, but these weird shapes here that we're spinning, sometimes it's like just kind of hard to draw. All right, you might be able to visualize it, but it's definitely hard to draw. All right, so in this case here, once again, we are going with the washer. So when we're going with the washer, we have to identify what's our big radius and what's our little radius. So the big radius is the distance from the axis that we're spinning around to the end of the region. Okay, so we're going all the way here. And notice that the top curve is y equals square root x. Okay, so this distance here, I'm going to call this big R, is going to be square root x. And I could just say square root x here. Technically, I should use the concept of top minus bottom, but this is the line y equals 0. So if I do y equals, we have square root x minus 0, that's just going to give us square root x. Okay, so this one here is perfect for us defining capital R, which is our big radius. Now for the little radius, that's the distance between the axis that we're spinning around and the beginning of the region, okay? So notice that when we draw one of our cross sections here, that we're first hitting the curve y equals x squared, okay? So that's our bottom curve here, y equals, and then we have x squared. So in this case here, the little r, so the little radius here, so we have little r is going to be equal to x squared. Now, one thing, the most common mistake with these questions is students just do something like this. They just do square root x minus x squared, but we're not finding the area between the curves, okay? We're finding the volume of the solid generated by revolving S about the x-axis, okay? So we just have to be very careful with this. So now what we're going to do is we take this cross-section here, and we're going to find the volume of this cross-section. So what we're describing is the volume of a single slice, okay? So let's just say we're describing this volume over here. So for this one, if the big radius is capital R and the little radius is lowercase r, we're going to have pi times, and then we would have big R squared minus little r squared. And in this case, we're going with dx because we have vertical cross sections, okay? So this little infinitesimally small change in the horizontal direction, we would call this component here dx if we're doing a vertical spin like this. Okay, so we have pi times big R squared minus little r squared dx. But now let's just think about what is big R squared. Well, big R squared, if we square both sides, that's just going to give us x. And then we have minus little r squared. If I do x squared squared, that's going to give us x to the fourth power. And then we have dx here. And now notice that this region, it starts at x equals 0 and it stops at x equals 1. If they didn't give us that information in the picture, what we could do is we could just set up the equation x squared equals square root x, and we could just solve this for all solutions. And the two solutions here would be x equals 0 and x equals 1. And this would tell us our limits of integration. But now from this step, to get the full volume, because this is just the volume of one slice here, we would have to integrate this from 0 to 1. So now we're going to use the fundamental theorem of calculus. We're going to say that the volume is capital V, and we're going to have pi times, and now we antiderive. The antiderivative of x is 1/2 x squared, and then we have minus the antiderivative of x to the 4 is 1/5 x to the 5th. And we're evaluating this from 0 to 1. Okay, so now we just use the fundamental theorem of calculus, where we finished using it, and we're going to plug in now. We're going to have 1/2 times 1 minus 1/5 times 1. So that's just going to give us a half minus a fifth, and then we have minus, we plug in 0, and we're just going to be subtracting 0. Both of those are going to wipe out. And now we just have to simplify here. We have pi times 1/2, if we multiply by 5 over 5, is going to work out to 5 over 10. And then we have minus, multiply this by 2 over 2, and you're going to get 2 over 10. So now we subtract here, and we're going to have 5 over 10 minus 2 over 10. And we'll just make that a little bit neater. That right now looks like a 6, so we'll just fix that. So we have 5 over 10 minus 2 over 10 is going to give us 3 over 10 times pi, or 3 pi over 10. And this is going to match up with choice C. Question 7, we have let W be the region in quadrant 1 bounded by y equals square root x, y equals 1, and x equals 1. And then we have which integral expression gives the volume of the solid generated by rotating region W about the line x equals 1. So for questions like this, when the picture is not given to you, I highly recommend that you draw this out. So we have y equals e to the x, and this is one of those functions that you should be able to sketch without a calculator. So you have y equals e to the x, and then we have the line y equals 1, so that's this line over here, so this horizontal line. And then we have the line x equals 1. Okay, so that's going to be, let's say, over here. So I'm not drawing this necessarily to scale, but it's just going to give us an idea of the region that we're going to be revolving. And we're going to be revolving this region around the line x equals 1. So not only is this part of our boundary here, but it's also our axis that we're spinning around. So once again, we're taking this region over here. So this is region W, and we're going to revolve it around the line x equals 1. So for this question here, what we want to think about is we want to think about which type of cross sections are we dealing with, because now we're going to be spinning around a vertical axis. So we're going to be dealing with horizontal cross sections. But notice this time around that the cross sections are resting on the axis that we're spinning around. So in this case here, we're going to be going with the disk. There's no gap between the region and the axis that we're spinning around. So our cross section here is going to be a disk. Okay, so this is going to be completely solid. And since we're spinning in the horizontal direction, we're going to be dealing with equations in terms of y. So the first thing I'm going to do now that we have this all set up is I'm going to take the equation y equals e to the x, and I'm going to solve it for x. So here I just take the natural log of both sides, and this tells us that natural log of y equals natural log of e to the x. But natural log of e to the x is just x. So this is just the way we're going to be writing this, because once again, we need to set up our equations in terms of y. Okay, so over here we have this equation is x equals natural log y. So we have x equals natural log y. And now from this step here, we have the equation for this line that we're spinning around is x equals 1. So we have to be able to describe any one of these cross sections in this region W here. And the concept is right minus left. Remember, if I want to find the horizontal distance between 2 points here, let's say I call this 5 and 8, the horizontal distance between them is 3, and I just do the thing on the right minus the thing on the left. So here, when I look for my radius, I'm going to have my radius here, so I'm just calling this distance here r. We'll just make that a little bit neater. So this distance we're calling r. I'm going to have my equation on the right in terms of y minus my equation on the left in terms of y. Now, technically, this doesn't have a y attached, but it's an x equals function of y. So I have the function on the right, so I have 1 minus the function on the left is natural log y. Okay, so here's my radius expressed in terms of our functions here. So now what we're going to do is we're going to say that the volume of a single slice is just pi times r squared and then times dy. Okay, so remember, the volume of a cross section when you have a disk like this is, we're just going to say dv is equal to pi times the radius squared, but then in this case we're working with dy since this is a horizontal disk. So now we're going to plug in our r value here is 1 minus natural log y. And now our goal is to look for the integral expression which gives the volume of the solid. But now we just have to think about the limits of integration. Notice that the region is starting at a y value of 1, okay? Because this was the line y equals 1 over here. So the beginning y value is 1. And now we just have to think about where do these curves here intersect. So what is the y value at this location? Well, this just think about. If you have the equation y equals e to the x, what happens when x is equal to 1? When x is equal to 1, so if I just plug in here x equals 1, that would give us y equals e to the first. Okay, so the point over here, I'll just write this coordinate off to the side, is the point 1 comma e to the first. So when we are integrating, we have to think about what is the lowest y value in our region here and what is the highest y value, because once again, we're dealing with a horizontal cross section. So we're going around in this direction here. So we're using everything in terms of y. So not only does our integrand have to be in terms of y, our limits of integration have to be in terms of y as well. So our lowest y value is 1 and our highest y value is e to the first. Okay, so this is going to give us our integral that we need. So now I could say the volume is just equal to, we have pi times the integral from 1 to e, and then we have 1 minus natural log of y squared, and then we have dy attached at the end. So now we just scan the answer choices here, and this is going to match up with choice D. Question 8, let S be the region bounded by the graphs of y equals x squared and y equals 4. S is the base of a solid whose cross sections perpendicular to the x-axis are equilateral triangles. Which integral expression represents the volume of the solid? So for this question here, what we need to do is first, let's just draw a cross section that's perpendicular to the x-axis. Okay, so they're going to be facing this way like this. And our goal is to find the volume of the solid whose cross sections in this region here are turned into equilateral triangles. So this might be a little bit tricky to visualize. What I'm seeing here is that we have these cross sections and then we're turning them into equilateral triangles. So if we just did this indefinitely, we just kept doing this forever and ever, we make these infinitely thin cross sections and we just keep drawing them. This is the solid that we're starting to make. And I can't imagine what this looks like in the real world, but this is our solid that we're finding the volume of. Okay, so what I like to do for these questions is I take the cross section, I draw it off to the side, and I turn it into the shape that they want. So they want us to turn this, let me just make this a little bit neater. They want us to turn this into an equilateral triangle. Okay, and it's going to be slightly 3D because this is, like, remember, infinitely thin. So this distance here we're calling dx. Okay, that's the distance that we're going to name over here because this small change in the horizontal direction is a small change in the x direction, so we're going to call that dx. And now the vertical distance, we're going to say top minus bottom. The top equation is y equals 4, and the bottom equation is y equals x squared. Okay, so the sides here of this triangle, since it's equilateral, we're going to say is 4 minus x squared going all the way around. Now, our goal here, once again, is to find the volume of this solid. But in order to do that, we have to know what is the area of this equilateral triangle. So there's a nice formula that I like to use. To find the area of a triangle, I like the trig formula 1/2 AB sine C. Okay, so this is when I have some triangle. Let's say I have some triangle over here, triangle ABC. And the side lengths I'm going to call lowercase a, lowercase b, and lowercase c. That if I know one of the angles, let's say over here at C, that I could do 1/2 AB sine C, where A and B are the sides that are creating angle C. So since this triangle is equilateral, each of these angles is 60 degrees. Okay, so I know we said for the AP test you want to be in radians the whole time, but I'll just put this in degrees for now because we're not actually going to use the calculator for this. We're just going to be using it like this setup over here to create our integral expression. So now the volume of this solid, so of this specific cross section over here, this little slice, is going to be, we're going to have 1/2, and then we have AB, but notice that A and B are the same. They're both 4 minus x squared. So I could say 4 minus x squared, and then this quantity here is being squared. But now I'm going to multiply by sine of the angle between them is 60 degrees. Okay, if you want to write pi over 3 instead, just so that you keep everything in radians, then go ahead, call that pi over 3. All right, and then the thickness here, dx, just gets tacked on at the end. Because remember, this is just the area of the triangle, but dx is that third dimension that gives it volume. So this is the volume of a single slice. So if we want to find the volume of the entire thing, we have to think about where does this region start and stop. Now, from the picture, it looks obvious here that this is going to happen at -2 and 2. But if you needed to find this out more, directly, what you could do is you could set these two equations equal to each other. You set x squared equal to 4, and then you're going to subtract 4 on both sides. Or you could just use the square root property. If you just know here that when you take the square root of both sides, you're going to have x equals plus or minus 2, then this will be enough for you to find the limits of integration. Okay, so we're going to have x equals plus or minus 2. These are our limits of integration. So now we just go ahead and integrate from -2 to 2. And the integral over here, we're going to have to simplify a little bit. So now what we have, and let me just fix that. There was a stray mark here. So we have from -2 to 2. So we're just going to call this on the left the volume. Okay, so the volume is now the integral from -2 to 2. And we have 1/2 times 4 minus x squared, and then sine of 60 degrees or pi over 3 radians is square root 3 over 2. And then we have dx here. And now notice that when we do radical 3 times 1, we get radical 3, and then 2 times 2, we get 4. But notice that the limits of integration are not matching these answer choices. And it looks like what happened here is they're making use of symmetry. Notice that this function y equals x squared is even. It has symmetry over the y-axis. And this region here, notice that what we could do, instead of integrating from -2 to 2, is we could do the integral from 0 to 2 and then just multiply the previous integral by 2. Okay, so now I'm just going to go ahead and do that. I'm going to do 2 times, and now we have the integral from 0 to 2. And once again, we're just making use of the symmetry here. And then we have 0 to 2 times, on the inside of the integral, we have 1/2, and we have 4 minus x squared, and then we're multiplying by radical 3 over 2 dx. And then notice here that 2 times 1/2 just cancels out. So then all we're left with here, our final answer, we have square root 3 over 2. That's the only constant left. And then we have times the integral from 0 to 2. And now we have 4 minus x squared dx. And now we scan the answer choices and notice that this is going to match up with choice B. Question 9, we have a solid whose base is the region in the xy plane bounded by the graph of y equals 4 minus x squared and the x-axis. And then we have cross sections of the solid perpendicular to the x-axis are rectangles with heights equal to twice the length of the base of the rectangle. And we want to know what is the volume of the solid. So the first thing I'm doing for a question like this is drawing this out. And we have the graph of y equals 4 minus x squared, which looks something like this. This is one of those functions that you should be able to graph without a calculator or sketch without a calculator, just know y equals negative x squared looks like this, and you're just shifting it up 4 units. So the y-intercept here is going to be at 0, 4. And our x-intercepts, you could just do some quick algebra and see the x-intercepts are going to be negative 2 and positive 2. If you had to find it the long way, you could take 4 minus x squared and set it equal to 0. And if you had to, you could always just factor this as 2 plus x times 2 minus x equals 0. And this is going to give you solutions of x equals plus or minus 2. But either way, this is going to give us the x-intercepts of this region here. So this is the region here that we're going to apply Cavalieri's principle to. So now what I like to do from here is, since we have cross sections perpendicular to the x-axis, I'm going to take a single cross section over here. I'm going to draw it off to the side, and I'm going to build it up into the shape that they want. So they want to take this cross section here and turn it into a rectangle where the height of the rectangle is twice the length of the base. Okay, and now I'm just going to draw this in here just to give it some depth. And we're going to call this distance over here dx. And we're going with dx and not dy because we have vertical cross sections. So this small change in the x direction, we're going to call dx. And now the distance here, this part, we're going to use the top minus bottom concept. And remember, the top curve here is y equals 4 minus x squared. And the bottom, we have the x-axis. And just know the name of the x-axis, the fancy name of it, is the line y equals 0. So if I use the top minus bottom concept, 4 minus x squared minus 0 is just 4 minus x squared. But now what we're going to do is we have to describe the height. So I'm just going to give us a little bit of space. I'm going to move this over like this. Okay, so I'm just going to do this very carefully so I don't take too much. And now we're going to describe the height. And once again, the height is twice the length of the base. So I'm just going to multiply this base by 2. So I'm going to have 2 times 4 minus x squared. So now I have to describe the volume of the single slice. And the concept, one of the big ideas of Unit 8 is if you could describe the area or the volume of one slice, one cross section, you could find the volume or the area of the entire thing that you're looking for. Okay, so that's just like one of the big ideas that I use for almost all of those area volume questions. So now we have dv is equal to, and we're going to use the concept length times width times height. So we just multiply these three things together. So we have 2 times 4 minus x squared times 4 minus x squared is 4 minus x squared squared. And then we have dx. And now we're going to integrate, and our integral, and if we couldn't figure out the limits, and let me just draw that second integral behind the 2 because that's how all the answer choices look. But if we couldn't find out what the limits were, notice every answer choice, the limits are going from -2 to 2. So that's, this part here was not really like important, but let's say this shows up in the free response and you just have to be able to do this kind of stuff. This is, it does help to know algebra. Algebra is a very important part of the AP Calculus exam. So now we could just scan the answer choices. This expression here on the left is just going to represent the volume of the entire solid, okay? So I'm just going to erase that and call that capital V, where this represents the volume of the solid. And the volume of the solid is the integral from -2 to 2 of 2 times 4 minus x squared dx. So we're going with choice A. Question 10, we have a particle moving along the x-axis with velocity given by this function here for time t greater than or equal to 0. And we want to know which of the following expressions gives the total distance the particle travels from t equals 0 to t equals 4. So for this question here, the moment I hear total distance traveled, I just think here the distance is equal to, we have the integral from a to b, and then we have the absolute value of velocity, okay, on the inside of the integral. So that's automatically where my head goes. Anytime I have to find total distance, I want to use this formula. So now I notice we have a velocity function. So we're just going to find the total distance by setting up the integral from 0 to 4, and then we have the absolute value of our velocity function, which is e to the sine t, okay, over t plus 1, and then -1 outside the fraction, and then we close the absolute value, and then we tack on our dt. So now we just scan the answer choices, and notice this is going to match up with choice D. Now, choice A is very close, but this would actually tell us the displacement, okay? So just know that displacement is similar to this formula, but it's a different concept, okay? So displacement, this would be equal to the integral from a to b of just the velocity function. Okay, so in this case here, that would tell us displacement. And the idea behind it, if we just want to know what's the difference between displacement and total distance, if I had some guy and let's say he was walking, Okay, and let's say he takes 1, 2, 3 steps forward and goes 1, 2, 3 steps back. If he went 3 steps forward and 3 steps back, just so we make sure we have the concept down, his displacement would be equal to 0. But the distance, if this guy went 3 steps forward and 3 steps back, would be 6 steps. Okay, so that's the difference between displacement and distance. That distance is always greater than or equal to displacement. Okay, that we count backwards movement as total distance traveled. All right, so that's why it's going to be choice D and not choice A. Choice A is a very dangerous barrier. Question 11, we have a solid whose base is the region in the xy plane bounded by the graph of y equals sine x from x equals 0 to x equals pi and the x-axis. And then for this solid, each cross-section perpendicular to the line x equals pi over 2 is a semicircle. And we want to find the volume of this solid. So this question is definitely a bit tricky, but the first thing we want to do is draw this out. So let's go ahead and draw y equals sine x. And we only need to look at this from x equals 0 to x equals pi. So that's this space over here. So here's our sine curve from 0 to pi. And we're going to look at next the line x equals pi over 2, which is right in the middle. So this is going to be our line that we're going perpendicular to. Okay, so here's our line. And we're taking cross sections, once again, perpendicular to x equals pi over 2. And our goal is to find the volume of the solid that's created. So this might be hard to visualize, but like here's our region. And we're taking all of these cross sections here and turning them into semicircles. All right, so I don't know what I imagine this as. I think of that as like a block of cheese or something, but I don't know, whatever you could see that as, that's what we're finding the volume of. So for something like this is definitely a bit tricky. We have to be able to take this equation here. We have y equals sine x. And we're going to have to write this in terms of a function of y. Okay, so we're going to have to solve this for x. So we have y equals sine x. We're going to say x equals arc sine of y. All right. And now one thing to be very careful of, though, this question can go like pretty far, is that we are only allowed to consider this function on the space from 0 to pi over 2. And the reason I'm bringing that up is if I look at y equals sine x, if we want to talk about the inverse of sine x, we have to restrict the domain of sine x from negative pi over 2 to pi over 2. And the reason for this is if we look at a full sine curve, it just keeps going this way and this way. The sine curve fails the horizontal line test, which means it's not 1-to-1, which means it doesn't have an inverse unless we restrict the domain from negative pi over 2 to pi over 2, because that piece of the sine curve will pass the horizontal line test, and the range will go, we'll just make that neater, the range will go from negative 1-to-1. So I'm bringing this up because when I look at this inverse function, the inverse function, the domain and range switch. The domain goes from negative 1-to-1, and the range goes from negative pi over 2 to pi over 2. But notice that this space here from 0 to pi over 2 is fine. But I'm not allowed to go past from pi over 2 to pi. But that's not going to be a problem here, because when I look at these cross sections that I'm turning into semicircles, okay, these cross sections, notice that the center of these semicircles is going right up to the line x equals pi over 2. All right, so this is not going to be a problem for us. So this, we're going to describe the radius of each of these semicircles. So this equation over here, we're going to rename it in terms of x. So this is going to be x equals arc sine of y. And then we have this equation over here is x equals pi over 2. So now we're going to use the right minus left concept. The radius of each of these semicircles, we could say, is pi over 2 and then minus arc sine y. But now we have to be very, very careful how we describe the volume of one of these slices. Okay, so the volume of any one of these slices, notice we're going with small vertical changes here. So we're going to go with dy instead. But now I'm going to say the volume of one of the slices is going to be pi times the radius squared. Okay, so the radius we're going to square, and then we're going to divide this by 2. Okay, the reason why we're dividing by 2 is that this is a semicircle that we're turning this into. And of course, we multiply this all by dy so that it gives it volume. So we have pi times the radius squared dy, and then we're dividing by 2 because we have a semicircle. Okay, so just make sure that you're dividing by 2. So now from this step, we're just going to plug in our radius here. We have pi over 2. and then minus arc sine y. Okay, so minus arc sine y. Let's give ourselves a little bit of space, is going on the inside. Okay, so this is going on the inside. All right, so we have arc sine y on the inside like this. So this is just the volume of one slice. The volume of the entire solid, we just have to think about the limits, but the limits, since our integrand is going to be in terms of y, our limits have to be in terms of y. So the lowest y value is going to be at y equals 0, which all of the lower limits match, but we have to be careful with the next part. Okay, the upper limit, the top of the sine curve, the maximum value is 1. So we're going up to a y value of 1. Okay, so the full volume of the solid is on the left. So I'll just erase that and call that capital V. So the full volume of the solid is now equal to the integral from 0 to 1. And we have pi over 2, which we could write on the outside. So that eliminates these two choices here. And then on the inside, we have pi over 2 minus arc sine y in parentheses squared dy. So we're going to go with choice A. Question 12, we have a portion of the continuous function f of x, which consists of 3 line segments, is shown on the graph below. And we want to know what is the average value of f of x on this interval here. So we're going to use the formula for average function value, which is 1 over b minus a. So we have 1 over 5 minus negative 2. And then we're multiplying by the integral from a to b. So we have the integral from negative 2 to 5. And then we have f of x dx. So for this one here, first we could simplify 1 over 5 minus negative 2 is 1 over 7. So you have 1 over 7 times the integral from negative 2 to 5, and then we have f of x dx. But in this case here, we don't have an explicit function for f of x. If you want to, you could write the equation of these 3 lines and then integrate each piece, use the fundamental theorem of calculus 3 times, but that's going to take a really long time to do that. Your best bet here is just to use geometry, because remember, the meaning of this definite integral, just this part here, if we highlight this piece, the meaning of this definite integral from unit 6, we have to know, is this is the area under the curve, okay, the area under f of x from x equals negative 2 to x equals 5, okay? One thing to be mindful of, though, when I say area under f of x, technically I should say area between f of x and the x-axis, but that's what I mean when I say the area under f of x from negative 2 to 5. I should also mention here, it's the signed area. So in this case here, I could just get away with saying area because the f of x function is above the x-axis, but if at any point this had dropped underneath, we would have to treat the area under as negative, okay? So that's just something that we would have to be mindful of if it did happen, but in this case here, f of x is entirely above the x-axis, except at negative 2, it's equal to 0. So now, what we're going to do is just find the area of each of those regions here that we could create. So we're going to have this region over here, we'll just say is this right triangle. And this right triangle, notice the base, we just count the boxes, is going across 2, and it's going up to a height of 3. Okay, so we'd have 1/2, and then we have base times height, so we have 2 times 3. And then we're going to add this next region here. I could just look at this rectangle. And this rectangle, notice, is starting at x equals 0 and stopping at x equals 2. So the base is 2 units across, and the height is 1, 2, 3. So I'm doing 2 times 3. I could just count these boxes here since the scale is counting by 1 in the x and y direction, and there's 6 boxes. But I'll just go ahead and use all the geometry formulas. And now the last one here, we have this trapezoid, okay? And the region is ending at x equals 5. Now, if you know that the area of a trapezoid is equal to 1/2 height times base 1 plus base 2, then excellent. That's going to help you get through this fast. If you forget that formula, just know you could always chop this way and make a square and a triangle. I hesitated to say square because I just wanted to make sure this is a 3 by 3, which it is. But we would have a square and another triangle. Otherwise, if you know your formula for the area of a trapezoid, you could just get right to this. But just be careful here. The bases are the parallel sides. So normally we think about trapezoids, we think of these trapezoids here where they look like this and the bases are going in the horizontal direction. But in calculus, you're often going to encounter trapezoids that have bases going in the vertical direction. All right, technically I could have just even said that this is 2 shapes. I could have said this trapezoid where the bases are going horizontal and then this trapezoid where the bases are going vertical. But I don't know, I find it easier to deal with triangles and rectangles, so I chose to chop this one in this case. So now we have 1/2 The height is the distance between the parallel sides. So we have 1, 2, 3 is the distance between the parallel sides. And now I have the sum of the bases. Well, notice that this base here is going up 1, 2, 3, and this base is going up 5. So I'd have the sum 3 plus 5 going on the inside. Okay, so now I just have to work all of this out. So the rest is just arithmetic. Just make sure you don't, do some, silly mistake at this point. So now half of 2 just cancels. So I have 3 plus, and now I have 2 times 3 is 6 plus, and then on the inside here, I have 3 plus 5 is 8. And if I do 1/2 times 8, that's going to give us 4. So now we have plus 3 times 4 is 12. So now we just work this out. This is 1/7 times, and now we have 3 plus 6 is 9, plus 12 is 21, and 1/7 times 21 is going to give us 3. Okay, so this simplifies to 3, and this is going to match up with choice C. Question 13, let capital F of x be the antiderivative of f of x equals this function here. And then we have if capital F of 4 equals pi, then capital F of 1 equals. So for this question, what we're going to do is we're going to set up this integral, the integral of f of x dx, and we have to be very strategic with the limits that we use here. So the one that we know, I'm going to put 4 on bottom. We know what capital F of 4 is. So that's why I'm going to put my lower limit as 4. But I want to know what's capital F of 1. So now here, if we apply the fundamental theorem of calculus, we would take the antiderivative of f of x, and we were told here that the antiderivative of f of x is capital F of x. So this would be equal to capital F of 1 minus capital F of 4. Okay, so we're just using the fundamental theorem of calculus. We take the antiderivative of the integrand, and then we plug in the upper lower limit to the antiderivative and subtract. But our goal is to solve for f of 1, capital F of 1. So I'm just going to add capital F of 4 to both sides, and this tells us that capital F of 1 is equal to, and then we have capital F of 4, and then we have plus the integral from 4 to 1 of f of x dx. Now, for some students, this may bother you that this integral, the lower limit, is greater than the upper limit. And you can flip this and say capital F of 4 minus the integral from 1 to 4. But since we're going to be using the calculator for this question, it doesn't matter. We could just type this in as is. So now we're just going to work this out. We're going to say capital F of 1 is equal to, we have pi plus the integral from 4 to 1 of lowercase f of x is this entire function here. So we have x to the third minus cosine x plus sine x, and we're dividing this by e to the x. Okay, and then we just tack on our dx. So this is all going into the calculator. So now we just type this in. We have pi plus, and we have math 9. So that's going to pull up an integral for us. And our integral, we're going from 4 to 1. And now the integrand here, we're just going to press alpha y equals enter to pull up a fraction. And we have x to the power 3. And we press the right arrow to get out of the exponent. And then we have minus cosine x. And then we have plus sine x. And then we close the parentheses, and our denominator, we have e to the x. So we press second natural log, and we have e to the x. And now we just tack on dx. And this is going to work out here. This is looking like choice C. So capital F of 1 is equal to negative 0.467. Question 14, we have Alexia, and she wants to increase her social media following. At the start of the month, Alexia has 5,000 followers. And then we have the rate at which Alexia's followers are increasing each day is modeled by the function r of t. And the units for r of t is followers per day. And we're told t is greater than or equal to 0, and t is the number of days since the start of the month. And we need to determine the total number of followers Alexia will have 15 days after the start of the month, and we're going to round to the nearest whole number. Now, since we're looking for how many followers Alexia will have 15 days after the start of the month, we're going to be looking at the interval from 0 to 15, because the beginning of the month is at time t equals 0. Okay, so the start of the month is t equals 0. But now, one thing we have to be mindful of is that Alexia already has 5,000 followers. So we're going to be doing 5,000 plus. And now, since we're starting with the function r of t, and r of t is a rate, we're going to do the integral of the rate. Okay, so we're going to integrate r of t, and the limits of integration are going to be 0 and 15. Now, the reason why we're integrating is r of t is a rate, and the units are followers per day. So this is just going to help you understand the concept. So followers per day. But the units for dt are also in terms of days. So followers per day times day, notice that the units would cancel and it would just tell you how many followers. Okay, so that's why we're setting up this integral here. Okay, so now all we have to do is just type this in. So let's type in, we have 5,000 and we're going to add, we have the integral, so we have math 9, and the integral is going from 0 to 15. And then the function r of t, we're just going to copy this over here. We have 100 and we're multiplying by e, so we have second natural log, and the power of e is 0.1 times t, but we're going to just use x. And now we're multiplying that by natural log of 1 plus x squared. Okay, so 1 plus x squared. And now we close the parentheses and we tack on the dx, and here's our answer. So to the nearest whole number, our answer is going to match up with choice D. Now, one extra detail I want to point out. Let's say this concept of integrating the rate doesn't make sense. One thing you could do is you could define r of t to be equal to df dt, because r of t is the rate of change followers per day. So I could say df over dt. This is the change of followers over the change in time. And then if I want to find the number of followers, what I could do is I do a little algebra here. So this is bringing us back to unit 7. And I would do df times 1 is df equals, and I would have r of t dt. So if I were to integrate this, or both sides of this equation, from 0 to 15, what this would tell us is the number of followers that Alexia accumulates from t equals 0 to t equals 15. So this is just, once again, a little bit extra to explain why we're integrating capital R of t, because I think that concept in the beginning gets very confusing for students. Question 15, we have this figure below, and it shows a portion of y equals 1/2 x to the third, and then we have a rectangle with two vertices at 0, 0, and c0, and we want to know what is the ratio of the area of the rectangle to the shaded part of it above the cubic. So for this question here, let's first find the area of the rectangle. And the area of a rectangle is base times height. And we know this distance going across is c, because we're going from 0, 0 to c0. So the x is just changing by c units. But to find the height of the rectangle, we're going to have to plug into the equation. So when x is equal to c, we plug into the equation, and that tells us the y value here is 1/2 c to the third. Okay, so now I could find the area of the rectangle. I'm going to do the base, which is c, times the height, which is 1/2 c to the third. And now this is going to simplify here. The area of the rectangle is equal to, we'll have 1/2, and then c to the first times c to the third is c to the fourth. Okay, so this is one piece that we need. But now for the next piece, we need to know what is the area of the shaded region. And there's a few ways that we could do this, but one way to do this is to subtract this function here by this function here and then integrate. So notice that this is the horizontal line, y equals 1/2 c to the third. Okay, because notice that the height of the rectangle is 1/2 c to the third. So this horizontal line, since it's matching the height, would just be y equals 1/2 c to the third. And we're treating c as a constant in this question. So we have 1/2 c to the third is this equation, and then the equation here is y equals 1/2 x to the third. Okay, so now to find the area of the shaded region, I take a single cross section here. So we're finding the area between these two curves, and that cross section is a rectangle. And if I was to describe the dimensions of this rectangle, the horizontal space here I would call dx, and the vertical distance I would do the top function minus the bottom function. So I would say 1/2 c to the third minus 1/2 x to the third. So now the area of one slice, I could just say is 1/2 c to the third minus 1/2 x to the third, and then times dx, because I'm doing base times height here. But now I want to know what is the area of the entire shaded region, not just the area of this single cross section. So now I'm going to integrate here, and I'm going to integrate from x equals 0 to x equals c. Okay, so this is going to tell us the area of the shaded region. So now I'm going to say the area of the shaded region is equal to, and I anti-derive 1/2 c to the third, and I get 1/2 c to the third times x, because remember, c is a constant here. So I have 1/2 c to the third times x minus, and now when we anti-derive x to the third, that's 1/4 x to the fourth, but times 1/2 is going to give us a 1/8 here. So I have minus 1/8 x to the fourth, and we're integrating once again from 0 to c. So now I just tack on the limits of integration. And now we just go ahead and plug in. So the area of the shaded region is equal to, we plug in c for x, and we're going to get 1/2 times c to the third times c to the first is going to give us 1/2 c to the fourth. And then minus, we plug in c for x, and we're going to have 1/8 c to the fourth. And now minus, we plug in 0, and we get 0. So that part is going to be nice. So now we just have to subtract the fractions. So we're doing the area of the shaded region. I'm going to call this 4/8 c to the fourth, and I'm subtracting 1/8 c to the fourth. And now 4/8 minus 1/8 is 3/8, and then we have c to the fourth. So this is the area of the shaded region. So now we have to set up our ratio. So the ratio that we want is the ratio of the area of the rectangle goes first in the numerator. And now in the denominator, we have 3/8 c to the fourth. And the reason why we're doing this, remember, with ratios, the part that comes before the 2 goes in the numerator, and then after the word 2 goes in the denominator. Okay, so that's how we're setting up this ratio. Notice c to the fourth just cancels out, and now we can just multiply by the reciprocal of the bottom. We're using keep, change, flip, if you know that phrase. And we have 1/2 times 8/3, and then 8/2 cancels to make 4, and this simplifies to 4/3. But remember, to express this in this ratio form here, we could just say 4:3. And this tells us our answer is choice C. So now for the BC only multiple choice. And for question 16, we have f of x, and we want to find the length of the graph of y equals f of x from x equals 0 to x equals 5. So for this question, we have to know the formula that the length of a curve from x equals a to x equals b is the integral from a to b of, and then we have the square root of 1 plus, and then we have f prime of x inside parentheses, and this quantity is being squared. Okay, so this is our formula for arc length. So for a question like this, we just have to plug in. So we're just going to have that the length of this curve is going to be the integral from 0 to 5, and we're going to have 1 plus, and then we have f prime of x going on the inside. Now, this is going to be a calculator question, so we don't have to find this derivative by hand. We can use the calculator for it. But if we had to find this derivative by hand, we would just use the quotient rule, and we would have e to the x, so we have the low function, times the derivative of the high function. So we have e to the x times 2x, and then we have minus x squared times the derivative of e to the x is e to the x, and then we would divide by e to the x squared. Okay, so if we had to do this the long way, we would go ahead and use the quotient rule. But in this case here, we're just going to use the calculator. So I'm just going to say 1 plus, and we have f prime of x squared. We'll just make that a little bit neater. So we have 1 plus f prime of x squared. So now we just close this out, dx, and then we could use the calculator. So first I'm going to show how to do this entirely with the calculator. So let's pretend I don't know how to take this derivative by hand. I'm going to press alpha y equals enter, and we have x squared in the numerator, and we have e to the x on bottom. So that's second ln to pull up e to the x, and then we just type in our x. And now once again, let's say I don't know how to do this derivative. I'm going to press math 8, and I'm going to write the derivative with respect to x. And let's say I don't feel like retyping y1. I'm going to press alpha trace, and then option 1 is y1. So this tells the calculator, take the derivative of this, but I just have to say x equals x. Okay, so now the derivative of y1 is in the y2 spot. So now I could go to the main screen, and what I'm going to do is I'm going to type in this integral as is. I'm going to press math 9, and we have the integral from 0 to 5. And now we just have to write on, in the integrand here, we have second x squared to pull up the square root, and we have 1 plus, and remember, I did the derivative in the y2 spot, so I could press alpha trace number 2, and then just square it, okay? And I do this, and I just tack on the x for the dx, and this is going to give us our solution right away, okay? So our solution is 5.117. But let's say you want to do this, the longer way. Let's say you found the derivative by hand. But if you get a calculator, please just use the shortcuts because it's going to save you a lot of time. But if I want to do this by hand, I could just press math 9, and I'm going from 0 to 5. And let's just see if our answers match up. We press second x squared to pull up the square root, and we have 1 plus. And now I'm going to put a parenthesis here because my derivative is a little messy. So I'm going to press alpha y equals enter to bring this part up. And we have e to the x times 2x, or I could just say 2x and then e to the x. And then we're going to get out of that exponent, and we're going to subtract x squared e to the x. And now in the denominator of this fraction is e to the x squared. So let's say I'll pretend here that I don't know that's e to the 2x. So I have e to the x on bottom here, and this part on its own is being squared. And now I get to the right of this, I close parentheses around the whole thing and I square that whole thing. Okay, so that's our derivative squared. But notice when we do this, we should get 5.117. And notice here we get 5.117. Okay, so either way, we're going to get choice C. So once again, we're going with choice C. Question 17, our last multiple choice question, we have let R be the unbounded region between the graph of y equals e to the negative x and the x-axis that lies to the right of the vertical line x equals 1. And we want to know what is the volume of the solid generated when the unbounded region R is revolved about the x-axis. So for this question here, we have this unbounded region and we're revolving it about the x-axis. So what we're looking at here, let's say I take a single cross-section. Since we're rotating about the x-axis, we're looking at the disk, okay? That's going to be our cross-section that we're going to use for this question, because notice that the region R is entirely resting on the x-axis with no gaps. So that's how I know that we're going to be using the disk here. So we only have to define a single radius, and the radius is going to be equal to the height of the function e to the negative x. So R, we could just say, is equal to e to the negative x. So here, if we had to describe the volume of a single cross-section, the volume of the single cross-section is pi times the radius squared dx, okay? So it's pi r squared dx, but I'm going to make the substitution. For r, we're going to have r is equal to e to the negative x. So now we could simplify this a bit. dv, we could say, is pi times, and then e to the negative x squared would give me negative x times 2 is negative 2x, so I'd have e to the negative 2x, and then dx like this. But notice that we are going to integrate from 1 to infinity because R is an unbounded region. It's going all the way this way, okay? So we're going to integrate this from 1 to infinity, but notice that we're dealing with an improper integral, okay? So to evaluate this improper integral, we'll pretend that this is a free response question and we'll practice using the right notation, okay? So this is, once again, just if this was a free response question, that I would go through the trouble of using all of this notation, okay? So I'm just going to rewrite this now as pi times the limit, and we'll make that neater. So we have pi times the limit as b approaches infinity, and now we're going to replace that infinity with b. So we have the integral from 1 to b, and we have e to the negative 2x dx. Now for this part, it helps to know this shortcut. Anytime you integrate something like e to the kx dx, just know that this is 1 over k e to the kx plus c. And the reason I bring this up is that I don't want to use a u substitution for this. These questions already take up so much like time and a lot of writing, especially in the free response. If this is multiple choice, this is multiple choice. So normally I would just pretend that I don't have to worry about notation, but I just want to go over how to write this with proper notation. I would just leave this limit here in terms of infinity and plug in infinity. But if it's the free response, you got to practice writing this with your limit notation, okay? But this really helps to know because otherwise I have to do a u substitution. And once again, this question is already taking a really long time. So from here, what we're going to have is pi times, and now we have the limit as b approaches infinity. And now we anti-derive. The antiderivative of e to the negative 2x would be negative 1/2, and then we have e to the negative 2x, okay? And our limits of integration here are 1 and b. So now we just plug in. So we have pi times, and we have the limit as b approaches infinity. And on the inside here, what I like to do for situations like this is I'm going to leave the negative 1/2 outside of parentheses, and then I could plug in the limits of integration and subtract. So this is just a nice little thing to do that it makes it easier to simplify, I think. So we have e to the negative 2x, but we're plugging in b, and then we're subtracting. We have e to the negative 2 times 1, so we're just going to have e to the negative 2nd like this. And now we just go ahead and simplify this limit. And to make this easier to simplify, I'm going to say pi times the limit as b approaches infinity. And on the inside, we have negative 1/2. And I'm going to change this to 1 over e to the 2b. So I'm just doing a little bit of algebra here because I think it'll make this limit easier to evaluate. And we're subtracting 1 over e squared. But now just think about this. So for this part, here's the thought process. The only part of the limit we have to be careful of is this part here with the 1 over e to the 2b. If I plug in infinity, 1 over e to the 2 times infinity, this is 1 divided by infinity, because e to the 2 times infinity goes to infinity. And when I have 1 divided by infinity, this is going to shrink to 0. So this piece here, the one I'm highlighting, that piece is going to shrink to 0. So this limit is going to simplify to we have a pi in front, and then we have times, we have, and I'm going to use parentheses instead. So we have pi times -half, and then we're multiplying that by what's left on the inside was -1 over e squared. Okay, the highlighted piece shrunk to 0. All right, let's make that 2 a little bit neater. So we have -1 over e squared. So now we have a negative times a negative is a positive. We have pi times 1 is pi. And then on bottom here, we have 2 times e squared. So you have pi over 2e squared. And this is going to match up with choice A. So now we move on to the free response, and we could use a calculator for both of these free response questions. And first up, we have Vin's Coffee Factory. And we have at this factory, the rate, that's the $1 million phrase right there, in kilograms per hour at which raw coffee beans arrive is modeled by the function C of t. And now we have t is measured in hours, and the hours of operation for the factory are between 0 and 8 hours. Then we have at the start of the workday, which is at t equals 0, the factory has 300 kilograms of raw coffee beans from the previous day. So during the workday, which is between 0 and 8 hours, the factory workers roast coffee beans at a constant rate of 120 kilograms per hour. Okay, so this is all the important stuff. And now we can get started with this. So for part A, what we want to find is what is the total amount of raw coffee beans that arrive at the factory during the workday. So for a question like this, we have to be careful. We have to make sure we pay attention to the language here. We are only looking for the total amount of coffee beans that arrive at the factory. So we don't have to consider how much coffee is already there from the previous day. We want to just talk about how much coffee is arriving. So here we're going to integrate the function C of t. And we're looking for how much coffee beans arrive at the factory during the workday. And the hours of operation are from 0 to 8. And now just make sure that you tack on this dt here. Now the reason why we're integrating, so let's just think about this a little bit. The units for C of t are kilograms per hour. Okay, and the units for dt, the change in time, like the units for time, are also in hours. So you see how here hours over hours cancel, and that would give us kilograms, which is correct for the units we're talking about when we want to find the amount of raw coffee beans that are arriving. Okay, we would measure that in kilograms. So that's why we're integrating here. So that's what we're going to do. But for this question, we could use a calculator. So we're just going to type this in. So we're on the main screen, and the first thing I would do is go to the y equals here, and we could just type in the function because we're going to need this function throughout the question. So C of t, we're just going to type this in. Now, before we move on here, I would just double check to make sure that you type this in correctly, because if you type it in incorrectly, that's just an annoying way to lose a point for making a typo. So this is looking good. So now we're going to go back to the main screen, and for part A, remember, our goal was to evaluate this integral from 0 to 8 of C of t. So I'm going to press Math 9 to pull up a definite integral, and we're going from 0 to 8. And now C of t we wrote in the y1 spot. So I'm just going to press alpha trace to pull up y1, and I'm going to type in y1 here. And now we just put it in the x. It doesn't matter that this is a function of time. We're going to use x, and the calculator is not going to mind here. It's going to give us the same answer that we would get if we use t. So now we just press enter, and here's our solution to part A. So now let's just write out the answers. So we have that the amount of coffee that shows up is equal to, we have 1,011 point, and then we have 777 kilograms. Remember, for the AP test in the free response section, you should be rounding to 3 decimal places. And just know that if you're not comfortable with rounding, you can just truncate after 3 decimal places. So you could just chop here at the 3 decimal place mark, and that will also count as full credit. So there's more than one acceptable response. But once again, I just prefer to round. So this is going to be our solution to part A. For part B, first we're going to find C prime of 6. And for this, we just use the calculator. So the fast way to do this, we're just going to press Math 8 to pull up a derivative. We're taking the derivative with respect to x because we wrote C of t as a function of x. And now I'm going to press alpha trace to put y1 here. And we're evaluating this derivative at x equals 6. Please, if they allow you to use a calculator, no one should be doing derivatives by hand in this section. Okay, so time is a very valuable resource at an AP exam. So make sure when you are in the calculator section to use these shortcuts because it will save you time. So here I just press enter, and this is going to give us the first part of our answer to part B. So we can round our answer to 3 decimal places. So C prime of 6 is equal to 9.509. And for the units here, the units we're going to say is kilograms per hour squared. And if you struggle with the units, one thing I like to think about is that C of t is measured in kilograms per hour. That was the units they started us with. So what you want to think about is if you're starting off with units of kilograms per hour. So let's just think about this. So the units for C of t are kilograms per hour. And if we were to take a derivative of this, so we take the derivative with respect to time, all that's going to do is just bump this up by a power of 2 on bottom. So the next unit would be kilograms per hour squared. Technically, I could say kilograms per hour, but that would simplify algebraically to kilograms per hour squared. And if you think about this, where did this come from? Before kilograms per hour would be just kilograms, which was the idea in part A. When we integrated C of t, that gave us an answer in kilograms. But now we have to interpret the meaning of this in the context of the problem. So now let's think about what is C of t. C of t is the rate in kilograms per hour at which raw coffee beans arrive at the coffee factory. So since C prime of 6 is positive, that means that C of t is increasing by this rate at t equals 6. So now we just have to write all that into a sentence. Now, one thing I want to mention before we move on, my thought process for how I write these sentences. When I think about C prime of 6 is positive, so this is what I'm thinking about. C prime of 6 is positive. This means that C of t is increasing, okay, is increasing at t equals 6. So that's like actually what's going on in my head as I say, okay, first, C prime of 6 is positive, means C of t is increasing at t equals 6. But then I think about what is C of t in the context of the problem. C of t is the rate in kilograms per hour at which coffee beans arrive at the coffee factory. So that's why then I just replace, instead of C of t is increasing, I just say the rate at which raw coffee beans are arriving is increasing by. And then I write the units for C prime of 6, which is kilograms per hour squared. Okay, so that's just my thought process for constructing these sentences. I just use this idea from applications of derivatives, but then I replace the function itself with the actual story version of the function from the question. So now for part C, we want to determine if the amount of raw coffee beans at the factory is increasing or decreasing at time t equals 6 hours. And we have to explain our reasoning. So we have to actually write a sentence here. So what I'm thinking about for this part is I'm going to compare the rate in and rate out at t equals 6. So think about what is the rate in function. They gave us the function C of t. C of t was the rate that raw coffee beans arrive at the factory. So that's our rate in function, C of t. So we have to compare C of 6. We're going to compare C of 6 to the rate out. And the rate out is a constant rate of 120 kilograms per hour. So in a situation where C of 6 is greater than 120, this means that the coffee beans are showing up faster than the workers are roasting them. And if you think about it, if the amount of coffee showing up is faster than the amount of coffee being roasted, then that means the pile of coffee or the amount of coffee is going to increase. Okay, if you just think about that very carefully, if the rate in is greater than the rate out, coffee is showing up faster than it's being roasted, then the pile of coffee beans is going to grow. In another scenario, so we'll just continue this thought over here, what we could have is we could have C of 6, so that is the rate at which coffee shows up at t equals 6. If it is less than 120, then that means the workers are roasting coffee faster than it's showing up. Then the amount of coffee left at the factory is going to decrease. Okay, so the pile of raw coffee beans is going to shrink if the workers are working faster than the coffee is showing up. So that's the thought process behind this. But for either case here, we're going to have to find what C of 6 is. So to find C of 6, we're just going to press alpha trace y1 to pull up the function C of t, and we're going to evaluate the function at t equals 6. So now let's look at C of 6. C of 6 is equal to 152.1688375. And this is a situation where C of 6 is greater than 120. So the amount of coffee or the amount of raw coffee beans at the factory is increasing. Okay, so now we just have to build our argument using this information. So now for part D, we want to know what is the minimum amount of raw coffee beans at the factory during the workday, and we have to justify our answer. So for this question here, let's write a function and we'll call it A of t. And A of T is going to represent the amount of raw coffee beans. Okay, so this is the amount, I'll abbreviate, of raw coffee beans. So now for this function, we'll give ourselves a little bit of space here. We're just going to have to consider first how much coffee was there at the beginning of the workday. And they told us in the beginning that at the factory, at the beginning of the workday, there's already 300 kilograms of raw coffee beans from the previous day. So for this particular day, we already have 300 kilograms of raw coffee beans to start with. And now we're going to add, we have the integral going from 0 to t because A of t is a function of time. So we have the integral going from 0 to t. And now this is where we have to consider the rate in minus the rate out. Okay, so we're going to do the rate in minus the rate out. Because if you think about it, the amount of coffee at the factory, we would find by saying how much coffee shows up minus how much coffee do they roast, the workers. Okay, so the rate in was modeled by the function C of t. Remember, C of t from the beginning was the rate that coffee beans arrive at the factory. So that's the rate in this case. But we just have to be careful. A little notation thing here. If we're making this a function of t, we have to make sure that we re-index in the integrand. I'm not going to say C of t, I'm going to say C of x. And now let's think about what is the rate out. Well, they told us in the beginning, let's just make this a little bit neater, that the rate out, the workers are roasting coffee beans at a constant rate of 120 kilograms per hour. So that's going to be our rate out that we're going to write over here. So we have C of x minus 120. And now we could close this bracket here. And I'm just going to tack on a dx at the end. But now if you think about it, what is our goal? Our goal is to find the minimum amount of raw coffee beans. So we are essentially finding the absolute minimum value of A of t. So now we could use the derivative concepts here. We're going to take the derivative of A of t. So we're going to find A prime of t. And now the derivative of 300 is 0. But when we take the derivative with respect to time of this integral here, we're using the fundamental theorem of calculus. So you can just imagine here, when we derive both sides, we're taking the derivative with respect to time of each piece. And when we derive this integral here, notice that we have a constant and a variable t up top. These pieces here essentially cancel out, and this will become C of t minus 120. Okay, so that's the concept behind what's coming next, that A prime of t is going to be equal to, we're going to have C of t and then minus 120. But if you think about this, what this is basically saying here, this is the rate of change of the amount of coffee. And it's once again just equal to the rate that coffee shows up minus the rate that the workers roast the coffee. But now since we're looking for the minimum amount of A of t, we're going to set this function here equal to 0. But now to solve this, what we're going to do, we'll make this a little bit neater, is we're going to use the calculator. So now what we could do is we could go back to the y equals, and here's y1. But I'm going to name A prime of t. Notice that it's C of t minus 120. And in the y1 spot, we have C of t. So I could just make C of t minus 120 by doing alpha trace y1. So that's C of t right here. And then minus 120. And now a nice little trick, what I could do is I could go over to the y1 equation. And I'm going to go up to the equal sign and press enter. Because when I look for the root here, I only care about when y2 is equal to 0. When I have C of t minus 120 equal to 0. So now watch what happens though. If I press graph, so I'm just going to press zoom 6 and pretend this is like just, graphing this all over the place. Notice that this gives me a lot of excess that I don't need. I only care about what's happening from 0 to 8. So I'm going to change my x minimum to 0 and my x maximum to 8. And now I press graph and notice here that I have exactly one root between 0 and 8. So I'm going to press second trace and then 0. So I'm tracing the 0. I go a little bit before the root on the left. I press enter. I go a little to the right after the root. I press enter again. And then I press enter a third time. And here's the solution to A prime of t equals 0. So now I'll just write out this answer. This is true when t equals, and then we have 3.837, and then we have 847. Just know that when you are rounding to 3 decimal places, you should do that at the very, very, very end. Try not to round to 3 decimal places throughout because that will throw off your final answer at the end by a little bit. And that's one of those annoying points that you don't want to lose. So now that we found the critical point here, what we're going to do is we're going to evaluate A of t at 3 locations. We're going to evaluate A of t at the endpoints, so at 0 and 8, but we're also going to evaluate A of t at this critical point here. So now for the first entry, we could just see that A of 0, if you were to plug in 0 for t, that A of 0 is equal to 300, which makes sense because they told us at the beginning of the workday, there's 300 kilograms of raw coffee beans. But now for these two values here, we're just going to use the calculator. So now a nice shortcut here, I could press second mode, and then I'm going to press second and then the minus sign here for the answer. And that's just going to copy what we had from the previous part here. And now this, I could do something, I could store this as the letter A. I could press store and then let's say alpha math. So that now every time I press A, it's just going to put that decimal value in for us. So now we're ready to plug in. We want to find the function A of t, the function value at t equals this value here. So notice that A of t is equal to this long expression. So I'm going to press 300, and then we have plus math 9 is going to pull up a definite integral, and we're replacing t with this value here, 3.837847. So remember, I stored that as the letter A, so I could just press alpha math and then store this. And now in this spot here, remember c of x minus 120, this we wrote as y2. So if I go back to the main screen here, all I have to do is put y2 in the integrand spot. So I'm going to press alpha trace and then y2, and now I'm going to tack on dx here. And this is going to give us one of our function values. And now for the function value at t equals 8, all I have to do is go up to what I wrote here and press enter. And I'm just going to replace the a value at the top with 8. And that's going to give us both function values all at once. So now we'll just transfer the values to the table. And now we just have to interpret this table here. What is the minimum amount of coffee at the factory during the hours of operation? The absolute minimum amount of coffee occurred at this middle time here. The minimum amount of coffee was 258.661 kilograms. Question 2, we have S is the region in the first quadrant bounded by the graphs of f of x and g of x. And the first thing we want to do is find the area of S. So notice that S is the area between two curves. So at some point, we're going to have to find the points of intersection because that'll tell us where S starts and stops. And then another thing we have to know, which function is the top function and which function is the bottom function. So looking at f of x and g of x is a linear function. So I think it's pretty obvious here that g of x is this bottom function. And f of x has the exponential function e in it. So that's how I know f of x is the curved piece on top like this. But we get a calculator for this question anyway, so we could always type this in to be 100% sure which one is which. And now for this question, we're going to go with vertical cross sections to find the area between these two curves. So the vertical cross section here, if I zoom in over here, is going to form a rectangle. And the height of the rectangle, I'm going to use the top minus bottom concept, is going to be f of x minus g of x. And then this little horizontal distance here, this little change in the x direction, we're going to call dx. So to answer part A, we want to find the area of S. The area of S, we're going to set up the integral. And the integral we're going to have on the inside here, our integrand is going to be f of x minus g of x dx. But now to find the limits of integration, we have to know where does this region start and stop on the x-axis. So let's say it starts at x equals a and it stops at x equals b. We have to find the value of a and b. So to get the value of a and b, we're just going to type f of x and g of x into the calculator. So now we press graph, and notice we have all this extra space over here. I reset the window settings so we could practice adjusting it as we need it. So we are in the first quadrant, so I'm going to switch the x minimum to 0, and I'll switch the y minimum to 0 as well. And now let's see how this looks. So this is much better, but notice we still have this wasted space over here. Notice that the graph, we really don't care about what's happening after x equals 7. So for something like this, maybe I switch the x maximum to 7. And now I press graph, and this is a much better picture. So once again, we needed to know what are the coordinates for the 2 points of intersection. So we're going to press second trace number 5 for intersect. And I'm going to go up to the first point of intersection, and I'm going to press enter 3 times. And this gives me my first point of intersection. So I'm just going to leave this over here because we're going to need this information throughout the question. Now, before we find the second point of intersection, I want to store this x value in the calculator because we're going to need to use this more than once. So I'm going to press second mode, and I'm going to press second and then minus here and press enter. And notice that our x value shows up that we need. And now I'm going to press store, and I'm going to press alpha math, and I'm going to store this value as the letter A. So now every time I write the letter A, it's going to input this value here that we need. And I'm going to do this because I don't feel like retyping this throughout the entire question. So now we go back to the graph, and we're going to press second trace number 5 to get the second point of intersection. So this second point of intersection, we just have to scroll, and we get over to this location here. and we're just going to press enter 3 times, and there is the coordinates for our second point of intersection. So now that we have the coordinates for our 2 points of intersection, I'm just going to go ahead and write our limits of integration in, and we'll make a little bit of space here because the limits of integration have a lot of decimals involved. So for this type of situation, I'm going to write all of the decimal places because I should only be rounding to 3 decimal places at the end. So I'm going to say here we have 0.833 in the rest, and then our upper limit here is going to be this x coordinate. And once again, we're going with the x values because our integrand is in terms of x. So we want to make sure that our limits of integration are in terms of x because we're essentially taking all of these vertical cross sections here and we're going all the way from x equals a all the way to x equals b. So now to get our answer, we just have to type this in the calculator. But one thing I want to do is I want to store this second x value as the letter b. So I'm going to press second mode and I'm going to press second answer, and there is our second value that we need here. And I'm going to press store and I'm going to press alpha, and then there's the letter B over here under the apps button. So now what I could do is I could just press math 9 and I could write A as alpha math, and I'm going to press to type in B, I'm going to press alpha, and then the apps button over here is where B is located. And now we have f of x minus g of x, but we wrote f of x in the y1 spot. So we're going to press alpha trace y1 minus alpha trace y2 is where we wrote g of x. So we type this in the fast way and we just press enter, and here is our solution to part A. So our answer to 3 decimal places is 9.621. Part B, we have region S is the base of a solid, and for the solid, each cross-section parallel to the y-axis is a square. And our goal here is to find the volume of the solid. So if we're going parallel to the y-axis with our cross-sections, that means we're dealing with vertical cross-sections. So this solid is definitely a little bit tricky to imagine. So what I'm imagining here is I have some solid, and I'm taking the cross-sections and building them into squares. So I did my best to draw region S somewhat like over here, a little bit tilted, but the solid that we're finding the volume of looks something like this. I can't imagine what this looks like in the real world. Okay, I can't imagine any sort of solid that takes this shape, but that's what we're finding the volume of. But the simpler way to do this is you just take the cross section and you draw it over here, and we're taking that cross section, so these vertical cross sections, and we're building them into squares. But notice, since we're dealing with vertical cross sections, the thickness of these cross sections we're going to call dx, because notice as we move left and right with our vertical cross sections, we have these little infinitesimal changes in the x direction. So we call those dx. And now the distance between these 2 points here, we're going to say is f of x minus g of x. So we're repeating that top minus bottom concept over here. So f of x minus g of x tells us the length of any one of these cross sections. But what we're doing is we're turning these cross sections parallel to the y-axis into squares. So that means the height of the square we could also call f of x minus g of x. So now in order to find the volume of the solid, we only need to be able to describe the volume of one of these cross sections. So the volume of one of these cross sections, we do length times width times height. We're going to be doing f of x minus g of x times itself. So at some point we're going to have f of x minus g of x squared, and then we're going to multiply by that third dimension dx. Okay, but this is just the volume of one cross section. We want the volume of the entire solid, so that's where we throw in the integral. And then for our a and b value here, for the start and stop, we're going to repeat the values that we used in part A. So now this we could just type right in the calculator. So we'll just press math 9, and A is still stored as this decimal value on bottom. So I'm going to press alpha math for A, and then we're going to press alpha apps for B. And our integrand is f of x minus g of x squared. So I'm going to put parentheses because I need to subtract these two functions inside of parentheses before I square. So I press alpha trace y1, and then we have minus alpha trace y2. So that gives us f of x minus g of x. And now I close the parentheses around f of x minus g of x, and I square it. And now I tack on the dx at the end, and this is going to give us our solution to part B. So now we'll write our answer, and we'll round to 3 decimal places. So we have 22.805. Part C, we have the horizontal line y equals k separates S into 2 regions of equal area. And we need to write but do not solve an equation involving one or more integrals whose solution gives the value of k. So for something like this, what I'm imagining right away is the line y equals k. Let's say it's at about this location, and that this line is cutting the region S into two sections of equal area. Well, if we need to set up an equation involving one or more integrals, we have to think about what type of cross sections we're going to use. And notice here that we have a horizontal line cutting this region in half. So that means when we describe the area of one or more of these sections, we're going to have to go with horizontal cross sections. So the first thing we're going to have to do here is a little bit of algebra, is we're going to have to describe f of x as a function of y, and we're going to have to describe g of x also as a function of y. So I'm just going to write f of x out in terms of y equals. So we have y equals, and we're going to have 8 minus e to the x minus 4 power. So now we just have to do algebra here to solve for y. So what we could do first is just subtract 8 on both sides. We have minus 8 on both sides. And now 8 minus 8 cancels. We have y minus 8 equals, and we have negative e to the x minus 4. So now we could just multiply both sides of this equation by negative 1. So I'll just write it like this. And what we're going to have is, we're going to have negative 1 times y is minus y, and negative 1 times negative 8 is positive 8. So we have 8 minus y is equal to, and then we have this side just turns into e to the x minus 4. So then from this step, what we could do to get e to cancel out, we could take the natural log of both sides. So we have natural log of 8 minus y is equal to, and then if I take the natural log of this side, notice once again I have natural log of e to the x minus 4, that the natural log and e are just going to cancel out, giving us x minus 4. So I'm just going to write that all in one line here so I could just solve this a little bit faster. So I'm just going to say x minus 4 on the right side. I'm just going to, once again, natural log and e just canceled out on the right. So now to solve for x, I just need to add 4 to both sides. So I'm going to have x equals, and we have 4 plus natural log of 8 minus y. So here is our function f of x described as a function of y. Okay, so we're just once again solving for x, because when we set up a horizontal cross section, we need to be able to use the concept of right minus left. So I need to have an equation as x equals a function of y. So now we're going to do the same thing, but we're going to do this for the second function. So you have y equals, this time around, negative 5/4 x plus 9. Okay, so we'll just make a little space here. We have y equals, and we've got negative 5/4 x plus 9. So this one we're going to solve for x now. So let's just make a little space here. So I'm just going to put a little dividing line also so we don't collide with what we did over here. So now we're going to subtract 9 on both sides. We have y minus 9 equals negative 5/4 x. And now to solve for x, we can just multiply both sides by the reciprocal. So we're going to multiply both sides by negative 4/5. And this is going to give us the equation for x for the second function. So we have x equals, and we have negative 4/5 times y minus 9. I could distribute, but remember, you're not graded based on how far you simplify in this part of the test. We're just going to set up the integral. We don't have to actually solve anything out. So this is more than enough for our two equations. So here's our first equation, and here's our second equation. So now let's describe the dimensions of one of these horizontal cross sections. So I'll make a little bit of space over here, and that's what we'll focus on over here. So one of these horizontal cross sections, I'm just going to draw it in, and I'm just going to say we're going to zoom in a bunch like this. And we have the vertical distance here, we're going to call dy. Okay, this represents a small change in the y direction. And now the horizontal distance, we're going to use the concept of right minus left. But notice that the function on the right is determined by the function that has curvature to it. So that's going to be this one that we solved over here, the 4 plus natural log 8 minus y. And the function on the left was the linear function. So that's going to be this function over here, the negative 4/5 times y minus 9. So this is essentially our x on the right, and this is our x on the left. So that's what we're going to use when we set this equation up over here, or the expression up over here. So we have 4 plus, and we've got natural log 8 minus y, and we're going to be subtracting. So we have minus, and then we're subtracting negative 4/5 times y minus 9. So we could see that our integrand here, when we set up our integral, is going to involve this as our integrand. We're going to have this expression times dy. But now one thing to be mindful of is we have to think, where does this region start and where does it stop? So we're going to have to go with this y coordinate over here. You see how we have y equals 1.6991429? We're going to go with this y value, and we're going to go up to the line y equals k. But now let's think about what we just set up here. We just described the area of one of these pieces here, but one of these pieces represented half of the area of region S. So if we want to set this equation up, that would give us something that gives us the actual value of K. We could just set this equal to 1/2 of the entire area. So we could say that this is equal to 1/2 of the entire area, and we could just use the integral that we had in part A, or we could just even say that it's equal to 1/2 of 9.621. Okay, so we're just going to use that answer that we had in part A in our solution to part C. But once again, just to summarize, this equation is good because if we were to actually work this out and integrate this, we would have an expression involving K on the left, and we would have this value on the right, and we would be able to use the calculator to solve for K. But the big idea for these questions, once again, this represents half of the area of region S, and on the right side, we have the entire area of region S, so we just multiply it by 1/2, and then we could say that these two expressions are equal.